Welcome, guys. This is the second part of control logic for our breadboard 4-bit computer. I will try to explain you the working of the control logic with the help of the load B instruction. This is the diagram of the 8 input OR gate. Let us see the diagram of control logic. I use these 74 series ICs. 2 bits of the instruction register are the most significant bit, whereas 2-bit counter sets the least significant bits. Now see the diagram for the 8 input OR gate. For this purpose we required 7 OR gates. Each OR gate IC has 4 OR gates in it. Therefore we required 2 OR gate ICs. All 8 inputs are numbered 1 to 8. Output of this I named A, B, C, D. Then X and Y, and final output is Z. See the working of the load A instruction. 2 steps for fetch and 2 steps for execution. Now you can see the use of OR gate into this control logic. 4 control signals for load A instruction Q0 through Q3 fed into 8 input OR gate. You can see that. Now please observe the execution of the instruction load B. First see all the micro instructions I labeled on the breadboard computer. Initially the step counter is 0 and instruction is also 0. This is the reset value of breadboard computer. When we press reset, all A register, B register, program counter, instruction register will reset to 0. Program counter out, memory address register in, RAM out, A register in, B register in, ALU out, and output register in, instruction register in. All these micro instructions are active low except program counter increment enable. This is what you are seeing, the control logic. OR gates 74 SC 4514 and all that stuff inside the control unit. NOT gate is used to invert the control signal. Whatever the signals we are getting from the OR gate, we require to invert most of the time. These are the instruction and steps indicator LEDs. This is the NOT gate used for the counter out and RAM address in control signals, which is active low signals, so we required it to invert. Next NOT gate we use for the RAM out instruction and also for the micro instruction register in. Let's program for the load B instruction execution. At the location 0 we stored the 1 and at the location 1 we stored the data 9, which is 1001 in binary. For the step 0, counter out and RAM address in micro instructions are active. This is the beginning of the 4-bit breadboard computer. First clock pulse will load the data into memory address register from the program counter. That is 0. Now RAM out, instruction register in and counter enable are active. Clock pulse will load the RAM content into the instruction register, that is 1. 01 is the load B instruction. You can see now again the counter out and RAM address in micro instructions are active. Program counter is 1 now. That will be the address of RAM when we give the next clock pulse. Now we can see the data of the RAM, that is the 9 on the bus, for loading this data into the B register. For this we have to give one more clock pulse so that we can get that data on the bus. Here it is. Now RAM out counter enable, and B register in micro instructions are active. Now we are at the final step, that is the step 3. We have completed the 3 steps from 0 to 2. Final step is 0111. This step, when we give the clock pulse, the data of the RAM which is on the bus will fade into the B register. Let us give the final clock pulse to feed the data into the B register. Okay, now we load the data into the B register. You can see that into B register we have 9 and into A register we have 0. 0 plus 9 is 9 on the ALU. I hope you understand. I'll make it more easy in the next video. Thanks for watching.